Hello everyone, my name is Islam and I will be your representative today for the topic of deep fast embedded capsule networks. So our content will be a brief introduction, literature review, and then we will speak in details about the proposed method, experimental results and analysis will be discussed, as well as a conclusion. So first of all, the capsule networks is a proven concept in the computer vision that simulates the human vision. And the capsule networks did a very great job, but they did not achieve state-of-the-art accuracies for complex data sets, and that's why deep capsule networks have been introduced. And despite the accomplishments in the capsule domain for both the deep caps and the capsnets, they are both still slow. And that's why in this work the deep fast embedded capsule network has been proposed. So first of all, convolutional neural networks did not have the the preserved spatial relationships between the features. And that's why, for example, if we look at this image, we can see that there are two different faces. One that has its features, the eyes, nose, lips, in place, while the other has its features misplaced. So the second image is distorted. Despite this fact, CNNs actually predicts that both images represents a face. Capsule networks recognize the distortion in the second image, and this is actually because of having a rich vector representation. As we see here, the capsule networks were tested on the MNIST dataset, and they produce the vectors in the following manner. Feature maps are divided into groups, and then these groups are divided into smaller units called the capsule vectors, and these capsule vectors actually have a depth of 8, and these capsules are multiplied using matrix multiplication with a transformation matrix that increases their dimension, producing digit caps, which are the class capsules in this case, because we are working on the MNIST dataset. The capsule networks actually did not give a high performance on complex datasets, and that's why deep caps was introduced, and deep caps reached state-of-the-art accuracy in the complex datasets such as CIFAR-10, and deep caps achieved this because they relied upon very deep architectures inspired from resonance. As we see here, this is an example of a 152 layer ResNet, a very deep architecture, and the ResNets used skip connections to avoid the problem of exploding and vanishing gradients, because during backpropagation partial derivatives are successfully multiplied. If these partial derivatives are small, then the gradient will become very small at the end, because when multiple small numbers are multiplied, the result will be much smaller, so the gradient might vanish. And on the contrary, if the partial derivatives are large, then the gradient at the end will be large, and it is called exploding gradient. Skip connections gave shortcuts for the backpropagation process to provide the gradient. So speaking about the proposed method, as we see that both deep caps and capsule networks are very slow. So the aim of the new proposed method is to do three things. The first thing is to preserve the state-of-the-art accuracy reached, to give higher speed, and also to produce a reduced complexity in the architecture and the number of trainable parameters. I just want to notify you about something. The 1D convolutions that will be mentioned later are actually used for having a compressed and embedded encoding for the features. The 1D convolutions are not used for feature extraction directly. They are rather used for having a compressed embedded representation between the relationships of the features, and we will speak in detail about this. So here, as we see, there are three new blocks added to the well-known architectures. The three new blocks are actually shown here in the figure. As you see, there are 4 capsule cells which were actually made of convolutional capsules similar to the deep caps architecture, and then we have the fast embedded capsule cell containing of 3 new blocks. The first block is the 1D convolutional capsules, where capsule vectors are produced, and these capsule vectors are an encoding of a compressed and embedded representation for the relationships between the features, and then the output capsules go into the merged flat capsule layer, and the merged flat capsule layer actually measures both capsules coming from the skip connection and from the previous direct layer into a 2D matrix where the number of the capsules is the first dimension and the second dimension is the dimension of each capsule vector. After this, these capsules are inputted into the class capsules layer where the new dynamic routing process happens. And to give more details about this, as you can see, the first feature maps introduced are colored in green, because here the input to the FE capsule are these 2 green arrows. So the input, as you can see here, enters the 1D convolutional capsules, and using 1D convolutional operations we have an embedded representation here for the capsules, and the features are stacked over each other. So these 32 features, these are not 32 features, these are 32 relationships between the features. And then we extract from this 4x4x32 feature map 1632 capsule vectors made of relationships between the features, and then we merge both the features or the capsule vectors from the skip connections and the capsule vectors from the previous direct layer into this 2D matrix, and then we repeat them 10 times because the next capsule layer has 10 classes, and we need the predictions of each capsule vector for the 10 classes. And after this we do an element-wise multiplication transformation process, because we do not need now to change the dimension of the capsules. because as you see, the class capsule's dimension is similar. It is 32 as well. This is because intuitively the parent capsules, which represent the whole, and the child capsules, which represent the part, should share the same number of dimensions, because we live in a 3D space, and if these dimensions refer to the pose, then both should have the same number of dimensions referring to their pose, because they are in the same 3D space that we live in. Now, regarding the experimental result and analysis, the experiment was carried out on two different datasets: the C4 dataset, which is considered a complex dataset, and the FMNIS dataset, which is considered a simple one. And the experiments were carried out on the Google Colab platform. Regarding the C410, as we see, it is made of 10 classes. These are sample images, and it consists of 60,000 images. 10,000 are for testing. Now, regarding the analysis, as we can see here, the proposed method excels in the average epoch time. It is the fastest among multiple capsule domain methods, and it also excels because it has the least number of training parameters among all the capsule domain methods mentioned here in the table. But it actually comes in the second place when compared with the diverse enhanced capsule networks. So I think that it maintained a state-of-the-art accuracy here, because the difference is a small margin. It's about 0.21% the accuracy for the C4 dataset. Regarding the FMNIS dataset, it's a simple dataset that speaks about 10 different fashion items as classes. It also has 60,000 images in total, and 10,000 of them are for testing. Now, regarding the results and the comparison between the proposed method and the other class domain methods, as we see, the accuracy also here comes in the second place after the deep capsules 7 installments method, but it also still excels in the speed and in the reduced complexity referred or measured by the number of trainable parameters here. And also the reduction in the accuracy between the new proposed method and the deep capsules is around 0.04%. So as a conclusion, a new architecture called Deep Fast Embedded Capsule Networks has been proposed. It is made of 3 different blocks: the 1D conv-caps layer, the new dynamic routing, which is which relies on a fast and element-wise multiplication transformation process, and the merged flat caps layer that merges the skip connection capsules with the direct previous capsule layer. Experimental results on C410 FMNIS dataset confirm excellent properties: 58% reduction in trainable parameters and 64% decrease in the average epoch time in training and testing processes have been realized. So I would like to thank you so much for having me, and have a lovely day ahead. Thank you and goodbye.